Hello again. So far for limits, we've been relying on numerical or graphical techniques to evaluate them, right? So using calculator tables or using a given graph. But now we want to learn some analytic methods. How can we just manipulate the symbols, use algebra, use trigonometry to find these limits? We have to have some basic properties. We have to use some things we've learned in the past, and we're going to use some trickery along the way. But first I'm going to start with some of these basic properties, things that we know are true. So let's if we let b and c, let them be constants, and let's let the limit as x approaches c of some function equal L, and the limit as x approaches c of some other function g of x equal k. So we have some other limits that are already defined, that we've already figured out. All right, and b is a constant and c is a constant. All right, the limit as x approaches c of a constant. So if we have a constant function, now remember, what is a constant function? A constant function, recall, is like, if this is the b value, then here's the constant function, right? This is my x-axis, and there's the constant function, and here's c. Well, it doesn't matter if we approach c from the left or c from the right. The value at c, or the value as we approach c, is going to be that b value. Now, the limit as x approaches c of x, well, this is an identity function, a basic line. So what this says is, if x is approaching c of the identity function, as x gets close to c, the value of x is going to get close to c. All right, now, the limit with x approaching c of f of x plus or minus g of x. So if we have multiple things that are being added together inside the limit, what can we do with this? It turns out we can just break the limit up. This is the limit with x approaching c of f of x, plus or minus, depending on what we're given, the limit with x approaching c of g of x. And if we've defined those as L and K earlier, then this would be L plus or minus K. Now, here we have the limit with x approaching c of some constant times f of x. So if we have a constant times a function and we're taking the limit, we are allowed to bring the constant outside of the limit. So this is b times the limit with x approaching c of f of x. And so then this would be b times L, whatever that limiting value is. If we're multiplying functions and then taking the limit, we can again break that up as a product of limits. This is the limit with x approaching c of f of x times the limit with x approaching c of g of x, or L times k. And again, if we're dividing functions, it works the same. We've got to be a little bit more careful here. This is equal to the limit with x approaching c of f of x over the limit with x approaching c of g of x. But there's a condition we need here. Can you think of the condition we need before I say it? Remember that we can't have a 0 in the denominator. So then this is equal to L over K, provided K is non-zero. And finally, if we have the function raised to the nth power and we're finding the limit, powers work out nicely as well. This is the limit with x approaching c of f of x, and we would raise that whole thing to the nth power, or L to the nth power. So as long as we have these predefined limits, normal arithmetic behaves nicely over those limits. All right, so there's some some theoretical stuff here, but let's see an example. So here, we're told that the limit with x approaching 2 of a function f of x is 7. The limit with x approaching 2 of a function g of x is 3. We're asked to find the limit with x approaching 2 of 4f of x plus g of x squared. All right, so I can use the properties of limits that we saw in the previous topic. I can break up this addition, I can break up this multiplication, and I can break up this exponentiation. And so what I can do is I can write this as follows. This is equal to 4 times the limit with x approaching 2 of f of x plus the limit with x approaching 2 of g of x squared. Now the limit with x approaching 2 of f of x has been defined as 7. The limit with x approaching 2 of g of x has been defined as 3. So this is 4 times 7 plus 3 squared. Simple arithmetic now, that's 28 plus 9, 37. Now here we're asked to find the limit with x approaching 3 of 2x squared minus 4x plus 5. Using the limit rules, I could write this as twice, 2 times the limit with x approaching 3 of x squared minus 4 times the limit with x approaching 3 of x plus the limit with x approaching 3 of 5. All right, so using the properties that we saw on the previous page, I can break it up like this. Now, the limit with x approaching 3 of x, if we go back to our previous slide, that matches this rule right here, right? That's the identity rule. The limit with x approaching c of x is c. So the limit with x approaching 3 of x, this is 3. Similarly, this limit, the limit as x approaches 3 of x, is also 3. Now the limit as x approaches 3 of 5, 5 is a constant. And so again, if we go back to our previous slide, the limit with x approaching c of a constant is the constant. So this limit is 5. So this ends up being 2 times 3 squared minus 4 times 3 plus 5. And now if we look at that, isn't that just, if this is the function f of, if I called this some function f of x, isn't this expression just the function evaluated at 3? All right, I'm just replacing the x with 3. Simple arithmetic now. That's 2 times 18, look, that 36. 36 minus 12 is 24. 24 plus 5, this is 29. But again, this is just the function evaluated at 3. So why are we going through all this work with these rules if I can just substitute? Well, we've got to be careful. There are some situations where we can substitute, and there are some situations where we can't. And so it's a good idea to be aware of when we can just plain old substitute and when we can't. So let's talk about that some more. There's some friendly limits in a sense. Polynomials are very nice when we're evaluating limits. So for example, if p of x and q of x are polynomials and c is real, right, just a number on the number line, then the limit with x approaching c of a polynomial function is simply the polynomial function evaluated at c. Now if we have this rational function, If we have p of x divided by q of x, if we have a rational function and we're calculating the limit as x approaches c, then this is also p of c divided by q of c. Again, we have to be careful here, though, as long as, or where, q of c is not 0. So this is legal. We are allowed to just substitute as long as we have a polynomial function, or if it's a rational function, as long as the denominator ends up being non-zero. If the denominator ends up being 0, then we have to do some other stuff. So for example, if we have the limit as x approaches 2 of 3x squared minus 4x plus 5 divided by x squared minus 6, we can quickly look at the denominator and say, okay, if x was 2, 2 squared is 4, 4 minus 6 is not 0. So we can use a direct substitution. So then this ends up being 3 times 2 squared minus 4 times 2 plus 5 over 2 squared minus 6. So that's 3 times 4, that's 12. 12 minus 8 is 4. 4 plus 5 is 9. 2 squared is 4. 4 minus 6 is negative 2. I would write this as negative 9 halves. That's it. Easy arithmetic. Again, as long as the denominator doesn't end up being 0. If the denominator ends up being 0, we have other concerns. So there's some other nice functions, more friendly limits besides just polynomials and rationals. All of the functions that you've learned how to deal with in algebra and trigonometry are nice functions as long as we are in the domain of the given function. So for example, the limit as x approaches c of sine x is simply the sine of that c value. Similarly, for the cosine function, cosine of the c value. And if the limit is x approaches c of the tangent function, tangent of the c value. Now again, we have to remember things about the tangent function. You know, the tangent function had a restricted domain. So we have to be aware of that. For example, I couldn't substitute pi over 2 in here because the tangent of pi over 2 is undefined. So those are things that we have to be careful about. If we have an exponential function, if we have some base to the x power and we let x approach c, that's a to the c. If we have a logarithmic function, it's the log base a of c. All right, so all those functions you learned about in algebra and trigonometry behave nicely as long as we're on the domain of the function. So for example, let's take a look at these. If we wanted to find the limit with x approaching pi over 2 of sine x, well, the sine function has, the domain is all reals. So we have no restrictions here. The sine, so the limit as x approaches pi over 2 of sine x is sine of pi over 2. And if you remember something about the unit circle, the sine of pi over 2 is exactly 1. If we had the limit with x approaches e of the natural log of x, this is a logarithmic function. The domain of the logarithmic function is 0 to infinity. So e is certainly within the domain. And so then this would be the natural log of e, which also happens to be 1. Right, because that's the logarithm base e of e, right? So remember, all right, logarithm base e of e to the first is 1, right? That's how logarithms work. Now, let's look at this one. The limit with x approaches 0 of sine x over x. Now, I can calculate the sine of 0, 0, but the denominator is also 0 if I let x approach 0. So here, if we did something with this, here we get a 0 over 0. Hey, there's a division by 0. That's a concern. This is actually called an indeterminate form. These are tricky. We're going to learn some techniques on how to deal with indeterminate forms in this topic and in a later topic in the course. So let's talk more about indeterminate forms and see how we can deal with them. But this one's actually a very tricky example. We'll see this one later on in this section, but it's going to take a while to prove this limit. All right, so indeterminate forms. Generally speaking, indeterminate forms are expressions or limits of the form 0 over 0, infinity over infinity, 0 times infinity, 1 to the infinity, infinity minus infinity, and infinity to the 0. These are all called indeterminate. And they're called indeterminate because depending on the actual expressions in play in the numerator and denominator, these can take on different values. And so we have to be careful on how we evaluate these. So let's consider this example. If we have the limit with x approaching 3 of x squared minus 9 over x squared plus 5x minus 24. If we try a direct substitution, if we try just letting x equal 3, let's see, 3 squared is 9, 9 minus 9 is 0. And then in the denominator, 3 squared is 9, 9 plus 5 times 3, 9 plus 15 is 24, and 24 minus 24 is 0. So this is a 0 over 0. This is indeterminate. So what do? We've got to use some trickery. So what this tells me is, well, what I know is I've seen expressions like this in the past, and maybe I can factor them. Let's see if we can factor this numerator and denominator. All right, so this is still a limit with x approaching 3. X squared minus 9 factors as x plus 3 by x minus 3. X squared plus 5x minus 24 factors as x plus 8 by x minus 3. Now, we are allowed to, at this point, remove, notice that there's a common factor of x minus 3. So now, we are going to remove the common factor and this is a legal move. We're allowed to do this since x is not equal to 3, it's only close to 3, right? We're evaluating a limit. Really what's happening is we're only letting x get close to 3 and seeing what happens. We're never actually letting x equal exactly 3 when we're doing a limit process. We're letting it get very close to. We're going to remove the common factor of x minus 3. So now this becomes then the limit with x approaching 3 of x plus 3 over x plus 8. Now there's no concerns. I can now let x approach 3 and actually, in a sense, substitute the 3. And so then this becomes 3 plus 3 is 6. 3 plus 8 is 11. This limit is 6/11. Now, if you were trying to do this on a calculator, you would probably get a decimal value, right? If you're trying a numerical technique, using numbers, substituting numbers close to 3, you would get a decimal number. But would you necessarily know that that decimal number was exactly 6/11? If you're very familiar with decimal representation of fractions, maybe you would get that. More than likely you wouldn't. You would get an approximation. This is an exact value. And mathematicians, we like these exact values over approximations in many situations. All right, so let's see some more examples. So the first two exercises here are actually quite similar to the example we saw on the previous slide. This last exercise looks a little different, but you can use a similar idea. So what I would recommend is that you pause these, pause here, and try these exercises out on your own. See if you can get them. All right, so if we let x equal 0, if we try to let x equal 0 in this first expression, x squared plus 2x over x squared minus 2x, we would get a 0 over 0. All right, so if we tried that, we are going to get a 0 over 0. That's no good. That's an indeterminate form. So let's try, like we did before, let's try some factoring instead. So this is the limit as x approaches 0. Notice that I can factor out an x in the numerator. That's x by x plus 2. And in the denominator, that's x by x minus 2. I can remove that factor of x, leaving the limit with x approaching 0 of x plus 2 over x minus 2. Now I have no concerns with that 0. If I substitute 0 now for x, I get 2 over negative 2, which is negative 1. And so this limit is exactly negative 1. All right, let's try the next one. If I let x approach 2, 2 squared is 4. 10 times 2 is 20. 4 minus 20 is negative 16, plus 16 is 0. 2 squared is 4. 4 minus 2 is 2, minus 2 is again 0. Again, I get a 0 over 0, an indeterminate form. Don't leave it like that. Limit, x approaches 2. See now, if you're bad at factoring, what I know is that x equals 2 is a 0 of each of these polynomials. So I must be able to factor these as an x minus 2 times something. Similarly, an x minus 2 times something. And then maybe it's just a little bit of trial and error. I know I've got to have another x to get the x square. Negative 2 times a negative 8 would give me a positive 16 in the here. And negative 2 plus negative 8 is negative 10. Similarly here, x minus 2 must be a factor. X plus 1 is the other factor. Again, I'm allowed to remove the common factor of x minus 2. This becomes then the limit with x approaching 2 of x minus 8 over x plus 1. Now I can let x approach 2. And letting x approach 2 is no longer a limit. This would be 2 minus 8. That's negative 6. Over 2 plus 1 is 3. That's negative 2. All right, and then this third exercise on this page, the limit with h approaching 0 of 4 times 3 plus h squared plus 6 by 3 plus h minus 54 over h. This one's a little different. I can clearly see I've got a 0 in the denominator, though. If I let h approach 0, that's clearly 0 in the denominator. Let's check the numerator. If I let h approach 0, 3 plus 0 is 3. 3 squared is 9. 4 times 9 is 36. 3 plus 0 is again 3. Times 6 is 18. So I have 36 plus 18, that's 54. 54 minus 54, again, I've got a 0 over 0 situation here. I have that indeterminate form. So I can't leave it like that. Let's see what we can do with this. Let's expand things. Let's use a little bit of algebra here. So then this becomes the limit with h approaching 0. 3 plus h squared. That's 9 plus 6h plus h squared. Binomial square. Let's remember something here. A plus or minus b squared. That's a squared plus or minus 2ab plus b squared. You've seen this in every single algebra class you've ever taken. If you don't know it by now, you better learn it. So I expanded the 3 plus h squared. Then I have 6 times 3 plus h minus 54, still over h. Distributive property. This is still the limit with h approaching 0. That would give me a 36 plus 24h plus 4h squared plus 18 plus 6h minus 54 is all divided by h. All right, let's see what we have here. There's that 36 plus 18 minus 54. Let's circle those. 36 plus 18 minus 54. If we add those up, those terms all go to 0. All right, those add up to 0. All right, so now I have the limit with h approaching 0 and combining like terms in the numerator. That's a 4h squared plus 30h over h. Now I can do some factoring. This is the limit with h approaching 0. That's h times 4h plus 30 over h. The common factor of h can be removed. This is the limit with h approaching 0 of 4h plus 30. Now there's no issues. I can now let h equal 0 exactly. Or get very, very close to 0, right? So that's 4 times 0 plus 30. The limit is 30. So those are some situations where if we have just polynomials in the numerator and denominator and we can't just use a direct substitution, then we have to do some algebraic manipulations. We have to expand or maybe factor to remove a common factor that's causing the 0 in the numerator and denominator. Now let's look at a couple other situations that we might need later on in the course. So sometimes we have expressions involving radicals or complex fractions that need to be simplified, or we need to find limits of them. So our first example here is if we want to find the limit with z approaching 6 of z minus 6 over 3z minus 2, the square root of 3z minus 2, minus 4. All right, so if we try a direct substitution, if we let z approach 6, then that would give us 6 minus 6. That's a 0 in the numerator. And in the denominator, that would be 3 times 6 is 18. 18 minus 2 is 16. The square root of 16 is 4. 4 minus 4 is 0. So again, we have an indeterminate form. All right, no good. Can't do that. Can't have an indeterminate form. So the trick that we do here is we rationalize the part of the fraction that has the radical. All right, and you hopefully saw this trick in your pre-calculus course. But what we can do is multiply both numerator and denominator by the conjugate of the radical expression. So the conjugate would then be the square root of 3z minus 2 plus 4 in the numerator and denominator. Now, why are we doing this? Well, if you remember something, if you multiply conjugates, if you have a plus b times a minus b, that's a squared minus b squared. And so here, if I'm multiplying these conjugates in the denominator, now the denominator will no longer have a radical in it. So then this becomes a limit with z approaching 6. Now the numerator, I could expand this out. I could FOIL and see what happens. I'm just going to leave it alone. Let's see what happens. If I just leave this alone, z minus 6 by the square root of 3z minus 2 plus 4. And then in the denominator, I would have 3z minus 2 squared, the square root of 3z minus 2 squared. Hey, that's going to give me a 3z minus 2. minus 4 squared, which is 16. Limit z approaching 6. Leave the numerator alone. And now in the denominator, if I clean this up, let's see, that's 3z minus 18. All right, now, if we were to try to substitute 6 at this point, we'd still get a 0 over 0. Notice I've still got the z minus 6 in the numerator, so if I let z equal 6, that factor goes to a 0. 3z minus 18, if I let z equal 6, that's 3 times 6 is 18. 18 minus 18 is again 0. Have we done any good here? Well, it turns out, even though it's still indeterminate, right? Even though right now it's still indeterminate, we're in a better situation than we were before, because now I can easily factor this denominator. So the numerator is still z minus 6 by the square root of 3z minus 2 plus 4. But now notice 3z minus 18 is 3 times z minus 6. I can remove the common factor of z minus 6. And so then I have the square root of 3z minus 2 plus 4 over 3. And now I can use a direct substitution of 6. If I let z approach 6, 3 times 6 is 18 minus 2 is 16. The square root of 16 is 4. 4 plus 4 is 8 over 3. 8/3. All right, and let's look at this next one. Here we have the limit with x approaching 7 of 1/7 minus 1 over x minus 7. A quick inspection tells us that we have an indeterminate form, right? This is a 0, right, over 0. All right, so again, what do? Well, we got to use some algebra. Let's use some trickery here. All right, so the trick for this one is what's called a complex fraction. And the trick for simplifying a complex fraction is to multiply the numerator and denominator by a common denominator. So if we look at the fractions, right, if we look at the 1/7 and the 1 over x, the common denominator I would use if I wanted to add or subtract them is 7x. So what I do here is I multiply both numerator and denominator by 7x. All right, I'm multiplying by 1 in the form of 7x over 7x. If I do this correctly, nice things happen. This becomes the limit. Still x is approaching 7. All right, 1/7 times 7x. 1/7 times 7x, that's x. 1 over x times 7x minus 7. Now look at the denominator. The denominator is x minus 7 times 7x. Notice that there's now a common factor of x minus 7 in the numerator and denominator. Remove the common factor. And so then this is the limit as x approaches 7 of 1 over 7x. I can now directly substitute. It's 1 over 49. All right, so that's the first part of this topic, where we are just focusing on some of the basic ideas and some of the algebraic techniques that we can use for evaluating some limits and some indeterminate forms. In the next half, the second half of this topic, we're going to see some more ideas we can use for some special limits.